between black hole physics and quantum computing. It's really strange, a remarkable thing for me.
We are currently observing the onset of a monumental transformation in human history, marking the early stages of a groundbreaking revolution. A shadow fell over the scientific community when a sophisticated quantum computing system, hailed as a game-changer, was unexpectedly shut down due to urgent emergency concerns. World-renowned theoretical physicist Michio Kaku revealed startling truths about the future of quantum computing. His revelations didn't stop there. Kaku also disclosed mind-blowing insights into extraterrestrial intelligence and artificial consciousness, shaking the global scientific community to its core, as these disclosures reverberated like a thunderclap. What led to the immediate deactivation of this advanced quantum system, and what groundbreaking information has Michio Kaku brought into public knowledge this time? Stay with us as we explore this emotional moment, where Kaku is visibly shaken, even moved to tears, after the abrupt halt of the quantum computing system. Throughout the 21st century, we've witnessed a cascade of radical innovations that have reshaped the very fabric of civilization. These developments have redefined industries and granted humanity capabilities that once belonged to the realm of science fiction. From the astonishing rise of artificial intelligence to the mysterious world of quantum computing, this era has been marked by one revolutionary breakthrough after another. Among these trailblazing technologies, quantum computing stands out as a particularly promising and transformative field. Initially dismissed as a speculative theory formulated by a small group of ambitious scientists, quantum computing has now developed into a highly advanced technology capable of achieving feats that were once considered impossible. The foundation of this transformation was laid in the early 1900s, with the emergence of quantum theory, an idea in physics that unraveled the strange behavior of atomic and subatomic particles. This theory set the stage for what would eventually become quantum mechanics, which in turn provided the theoretical framework for quantum computing. However, the idea of using quantum mechanics for computation did not gain significant attention until 1980, when visionary scientist Paul Benioff proposed a bold new direction. He suggested utilizing quantum systems, which exploit phenomena such as superposition and entanglement, to design a new generation of computational devices. These devices would perform tasks in ways that defied the capabilities of conventional digital machines. Benioff's daring idea was later expanded upon by physicist Richard Feynman, who in 1982 presented an intriguing vision of computers that would operate entirely on quantum mechanical principles. Feynman believed these machines would not just enhance existing technologies. They could solve problems so complex that traditional computers would be rendered obsolete in comparison. Though revolutionary at the time, his concept sparked the imaginations of a new generation of scientists. Still, it remained largely theoretical for several years. It wasn't until the 1990s that tangible progress began, as brilliant minds around the world took significant steps toward bringing Feynman's dream to fruition. Among these intellectual giants were legendary mathematicians like Peter Shor and theorists from the Einstein era who had laid the groundwork for this technological leap. A major breakthrough arrived in 1994, when Peter Shor introduced a quantum algorithm so disruptive that it sent shockwaves through the scientific community. This innovative formula demonstrated that quantum computers could be used to crack complex cryptographic systems and accomplish computational tasks beyond the reach of classical machines. Shor's work marked a turning point, triggering a surge of interest in the development of practical quantum devices. It took nearly another decade, but eventually the first hands-on quantum computers began to materialize. While rudimentary, these early machines represented the initial steps toward a technological revolution. One of the first pioneers in this endeavor was Isaac Chuang, who, in 1998, collaborated with Neil Gersfeld from MIT and Mark Cuban from the University of California to build a basic 2-qubit quantum computer. This experimental model, developed at Los Alamos National Laboratory, demonstrated the fundamental principles of quantum computation in action. However, in the grand scheme of things, this early prototype had limited practical application, as it could not address the pressing scientific challenges of the time. The most significant limitation was its scale. The system only included 2 qubits. In quantum computing, a qubit or quantum bit is the fundamental unit used for storing and processing information. The computational power of a quantum system increases exponentially as the number of qubits increases. To provide perspective, A 2-qubit device is almost insignificant when compared to the immense potential of a quantum supercomputer with 10,000 qubits. Yet, the true marvel of quantum computing lies not only in the number of qubits a system can contain but in the extraordinary properties of the qubits themselves. Unlike classical bits, which can only exist as either 1 or 0, qubits possess the remarkable ability to exist in multiple states simultaneously, a quantum phenomenon known as superposition. To clarify, a classical bit can only be a 1 or a 0 with no exceptions. In contrast, a qubit can represent both 0 and 1 at the same time. This extraordinary feature allows a groundbreaking revelation may completely shift the foundation of our cosmic understanding. This is not merely a tale of enhanced computation speeds, but rather an unveiling of a dimension so foreign, it hints at an alternate reality. A recent investigation proposes the possibility that humanity might not be solitary in the universe. Scientists claim they've detected 7 celestial bodies that could potentially be encircled by hyper-advanced extraterrestrial mega-engineering. This hypothesis defies core principles of existence, bridging concepts from decoding black hole mysteries to presenting serious threats to international cyber defense. Microsoft's leap into quantum innovation has left both scholars and cybersecurity specialists in equal parts admiration and apprehension. What are the ramifications for our species? The outcomes are simultaneously exhilarating and deeply unsettling. Physicist Brian Cox, known for his eloquent demystification of the cosmos, appeared visibly rattled upon encountering the implications of Microsoft's quantum progress. His declaration that the breakthrough was frightening was not uttered in passing. It was a stark acknowledgement of the dramatic transformation this technology could provoke in our grasp of the universe, our governing systems, and humanity's trajectory. At the core of Cox's intrigue lies Microsoft's Majera 1 chip, a pioneering quantum processor constructed from an exotic state of matter known as the topological phase. The key development hinges on the controlled detection and manipulation of a particle referred to as the Majorana fermion, theorized back in 1937, long regarded as a crucial but evasive component for stable quantum functionality. This entity, which serves as its own antimatter counterpart, enables the creation of topological qubits, units that are not only significantly more stable than traditional quantum bits but also inherently resistant to computational errors. Unlike conventional qubits, which are exceptionally delicate and require immense corrective mechanisms, these topological versions provide a far more robust and scalable solution for future computing. Consequently, Microsoft's accomplishment is being celebrated as one of the most pivotal strides in the quantum arena. Cox's reaction is not confined to the technical prowess involved. It encompasses the broader consequences. Quantum computers of this sophistication, such as the one powered by the Majera 1 chip, possess the capability to confront challenges once deemed impossible for human intelligence. This includes mimicking molecular behavior to expedite pharmaceutical advancements, formulating materials with regenerative properties, and even confronting pressing environmental hazards like the eradication of microplastics and persistent toxic compounds. Classical systems, even those operating at supercomputer scales, fall short of managing the combinatorial depth inherent in quantum-level complexities. Yet, with this immense potential comes an ominous counterpart: quantum computing's capacity to destabilize existing infrastructures, especially within digital security domains. The current cryptographic frameworks, including RSA and AES, derive their strength from the processing constraints of traditional systems. A mature quantum computer could dismantle these codes within moments, jeopardizing everything from individual privacy to geopolitical stability. This stark reality exemplifies how technological evolution can concurrently create vulnerability. Cox's unease reflects the dual nature of progress. On one hand, quantum computation embodies humanity's zenith in scientific endeavor, possibly granting access to the secrets of the cosmos. On the other hand, it compels us to grapple with critical ethical dilemmas and metaphysical considerations. What responsibilities accompany such boundless algorithmic power? How can we safeguard its deployment for collective benefit? Are we truly equipped to face the deeper truths that such power may unearth? This emerging frontier demands that we revisit not only our scientific understanding but also our philosophical placement in the cosmic narrative. Quantum computing introduces a level of potency unprecedented in the annals of information science, and the phrase unprecedented power is no overstatement. While classical systems rely on binary digits that operate sequentially, quantum systems harness qubits, capable of occupying multiple states simultaneously due to the unique principles of quantum mechanics. This quantum duality empowers these systems to explore computational landscapes that would take traditional machines billions of years to traverse. However, such monumental ability carries with it both immense promise and sobering threats. The cornerstone of this computational advantage is the phenomenon known as superposition, a state in which a single qubit can embody both 0 and 1 concurrently, thereby allowing simultaneous evaluation of all possible outcomes. As a result, quantum processors can manage vast data arrays in parallel instead of linearly. To visualize this, imagine deciphering a 4-digit PIN. A classical device would attempt each permutation individually, but a quantum engine would assess all combinations simultaneously, identifying the correct one almost instantaneously. Now extend this principle to simulations involving millions of variables, like drug interaction modeling or intricate supply chain logistics. These are operations that even our most powerful supercomputers would be unable to complete within any practical time frame. Yet, superposition is only part of quantum's unique arsenal. Another crucial element is entanglement, a quantum connection between qubits that remains intact regardless of distance. This entanglement allows instantaneous state sharing between qubits, greatly accelerating computational tasks. Furthermore, quantum interference is employed to magnify correct answers while diminishing erroneous ones, enabling quantum processors to excel at solving extraordinarily complex optimization problems. The potential real-world uses of this capacity are revolutionary. In healthcare, quantum systems could provide molecular modeling precision never before achieved, thus hastening drug development. Within material science, they might facilitate the creation of substances with remarkable traits, from regenerative polymers to hyper-efficient power cells. Even climate science stands to benefit, as quantum platforms are capable of processing the incalculable factors involved in Earth's ecological systems, thereby helping to forecast and counteract environmental crises. However, these boons are accompanied by profound hazards. Foremost among these is the looming threat to digital security. Contemporary encryption methods, particularly RSA, are built on the difficulty of factoring extremely large prime numbers, an arduous task for conventional systems. Yet, with the application of quantum-specific protocols like Shor's algorithm, these same tasks could be executed in mere seconds, rendering most of today's protective systems obsolete. Consequently, essential infrastructures such as financial transactions, government communications, and private data would become vulnerable unless we rapidly adopt cryptographic models immune to quantum attacks. Additionally, the extraordinary capability of these systems sparks deep philosophical debates. If quantum machines can replicate the universe at a fundamental level, what does that imply about our concepts of autonomy, identity, and the essence of reality itself? Visionaries like Brian Cox have speculated that one day these systems might emulate the cosmos so accurately that it challenges whether we are living in a simulation, a revelation with staggering implications. Despite such concerns, the allure of quantum progress remains irresistible. Industry giants like Google and Microsoft are in a high-stakes pursuit to command this transformative force. Microsoft's Majera 1 chip, capable of accommodating over 1 million qubits on a solitary unit, stands as a milestone in terms of both durability and scalability. With such hardware, the advent of quantum supremacy is accelerating rapidly. Yet as we navigate this new frontier, we must exercise deliberate caution, ensuring that our innovations serve the global community and mitigate emergent threats. Quantum computing's influence on global cryptography and data protection cannot be overstated. This technological advancement is poised to overturn every principle we've held about information security. Today's digital safeguards are anchored in algorithms so complex that traditional systems would need centuries to decipher them. Quantum devices, however, harnessing entanglement and superposition, could bypass these temporal limits with ease. This is especially critical considering quantum's capacity to run algorithms like Shor's at unprecedented speed, breaking codes that currently guard our most vital data. The implications are severe. Online banking, classified government intel, and private communication channels could all become susceptible to cyber intrusion and manipulation. This stems from quantum's innate ability to explore all potential outcomes simultaneously, completing operations in minutes that would otherwise remain unsolvable for eternity. The looming concern for cybersecurity professionals is the harvest now, decrypt later scenario, where hackers hoard encrypted files today, intending to crack them with quantum tools once those become available. Recognizing this looming crisis, governments across the globe are pushing to develop and adopt encryption techniques immune to quantum-based decoding. Known as post-quantum cryptography, these protocols rely on mathematical constructs believed to be resilient against quantum attacks. The U.S. National Institute of Standards and Technology, NIST, is at the forefront of this initiative, currently testing various algorithms in preparation for a universally accepted standard. Transitioning to these new cryptographic methods is imperative if we aim to safeguard confidential information in an age dominated by quantum computation. However, quantum technology's disruption extends beyond just encryption. The evolution of quantum networking, particularly through quantum key distribution, QKD, could make unauthorized surveillance nearly impossible by enabling perfectly secure communication links. Simultaneously, this same capability could empower malicious actors, allowing them to stay perpetually ahead of law enforcement, setting the stage for a perpetual digital arms race. This rapidly shifting landscape underscores the multifaceted nature of quantum's impact. As we approach this turning point in human innovation, collaboration across industries will be critical. Cloud service providers and technology developers must work together to forge hybrid platforms that blend traditional processing with quantum acceleration, while educational initiatives should cultivate a workforce ready to thrive in a quantum-informed society. Advances in quantum-safe encryption have the potential to bridge the talent gap in the field. While quantum computing poses challenges to existing systems, it also compels us to rethink the foundations of security. Embracing this challenge could pave the way for a more secure global infrastructure, one that is prepared for the massive computational transformations on the horizon. Through collaboration, innovation, and careful planning, the future of data security holds significant promise. The arrival of quantum computing has evoked both excitement and concern in equal measure. Its ability to revolutionize industries, solve long-standing problems, and unlock the universe's deepest mysteries is awe-inspiring. Yet, as physicist Brian Cox and others caution, this incredible power also comes with risks that could reshape the world in ways we may not be ready for. Striking a balance between hope and fear in the age of quantum computing requires an understanding of its potential benefits alongside a clear recognition of its dangers. On the optimistic side, breakthroughs in quantum computing, such as Microsoft's Majorana 1 chip, open doors to extraordinary advancements. With the capability to integrate millions of qubits onto a single chip, quantum computers could simulate molecular interactions with unmatched precision, potentially leading to medical breakthroughs like cures for diseases such as cancer and Alzheimer's. In the field of materials science, these computers could design self-healing materials or create catalysts capable of eliminating microplastics and forever chemicals, thus addressing urgent environmental issues. Quantum simulations also have the potential to revolutionize climate modeling, enabling policymakers to make data-driven, precise decisions to combat climate change. The potential for positive change is immense, and the quantum era could mark a pivotal chapter in human progress. However, alongside these promises, there is a looming shadow of fear. The same power that allows quantum computers to solve complex problems also threatens to destabilize global security. One immediate concern is cybersecurity. Current encryption methods, such as RSA, rely on mathematical problems that classical computers cannot solve within a practical timeframe. Quantum computers, however, using algorithms like Shor's, could break these encryption methods in mere seconds, rendering financial systems, government communications, and personal data vulnerable to exploitation. This has sparked a global race to develop quantum-safe encryption protocols, but the transition will take years, leaving a dangerous gap in cybersecurity. Beyond cybersecurity, the philosophical and ethical questions raised by quantum computing are profound. Quantum computers could simulate reality itself, challenging our understanding of existence and free will. These machines could also be weaponized, enabling advanced autonomous systems or destabilizing economies. The very structure of society could be reshaped by those who control this powerful technology, raising critical questions about equity, privacy, and global power dynamics. Striking a balance between hope and fear in this realm requires proactive measures. Governments, scientists, and corporations must work together to create ethical guidelines, develop quantum-safe encryption methods, and establish international agreements to prevent misuse. Public awareness is equally crucial, ensuring that society remains informed and engaged in decisions regarding the future of this technology. The quantum revolution is already underway, and how we navigate its complexities will determine whether it becomes humanity's greatest tool for progress or a source of unforeseen consequences. The simulation hypothesis, the notion that our reality might be an elaborate simulation, has long been a subject of philosophical debate. With recent advancements in quantum computing, this hypothesis gains newfound scientific relevance. Quantum mechanics, the foundation of quantum computing, operates on principles that defy common sense, such as superposition, entanglement, and probabilistic outcomes. These principles not only govern the behavior of subatomic particles but also suggest a deeper connection between computation and the very fabric of the universe itself. Could the universe be functioning as a vast computational system? Quantum computers, like Microsoft's Majorana 1 chip, are designed to simulate quantum systems with unparalleled accuracy. By leveraging qubits that can exist in multiple states simultaneously, these machines mirror the complexity of quantum mechanics itself. This enables quantum computers to simulate phenomena that classical machines could never approach, such as molecular interactions, black holes, or even the very early moments of the universe. If these computers are capable of replicating aspects of our reality on a smaller scale, it raises the question: could an advanced civilization create a simulation indistinguishable from reality itself? The simulation hypothesis suggests that if it is possible to simulate a universe with conscious beings, then it is highly probable that our own reality is, in fact, a simulation. The progress of quantum computing makes this question more tangible. For instance, Microsoft's development of topological qubits, which enable the integration of millions of qubits on a single chip, could provide the computational power to simulate intricate systems, from ecosystems to entire civilizations, governed by the same rules that shape our own universe. Despite these breakthroughs, quantum computers highlight the fragility of our understanding. The probabilistic nature of quantum mechanics, where outcomes are not determined until they are measured, raises deep questions about free will, consciousness, and the very nature of reality. If our universe operates like a quantum computer, constantly computing an array of possibilities, what does this mean for our sense of individuality or autonomy? While the simulation hypothesis remains speculative, quantum computing offers a unique perspective on these questions. Machines like the Majorana 1 chip do more than solve complex problems. They replicate the fundamental processes that govern the universe. Through quantum computing, we may not only unlock new technologies, but also uncover profound truths about existence itself. As scientists like Brian Cox suggest, these advancements challenge our assumptions about what is real and what might simply be the result of computation. Few phenomena capture the imagination like black holes. These mysterious cosmic objects, with their immense gravitational pull, represent some of the most profound enigmas in the universe. Thanks to advancements in quantum computing, scientists are now beginning to study black holes in ways that were previously unimaginable. Physicists, including Brian Cox, have pointed out how quantum mechanics and black hole research are becoming increasingly intertwined, offering insights not just into the nature of black holes, but also into the fundamental structure of reality itself. At the core of this intersection lies the concept of information. Black holes are infamous for their ability to trap everything within their event horizons, including light. But what happens to the information contained in the matter they consume? This question, known as the black hole information paradox, has baffled physicists for decades. Classical physics suggests that the information is lost forever, but quantum mechanics asserts that information cannot simply disappear. Recent studies suggest that black holes may store this information in a manner that aligns with the core principles of quantum mechanics. This is where quantum computing plays a critical role. Black holes are thought to function as natural quantum systems, processing and storing information at their event horizons. Quantum computers, which use qubits to process information in fundamentally probabilistic ways, offer a unique tool for simulating these interactions. For example, Microsoft's work with topological qubits, as seen in their Majorana 1 chip, enables researchers to model how quantum information might behave near a black hole. These simulations provide crucial insights into how black holes might encode and possibly release information back into the universe, particularly through phenomena like Hawking radiation. One groundbreaking experiment involved using quantum processes to simulate the behavior of entangled particles, mimicking how black holes might entangle quantum information at their boundaries. By applying the holographic principle, which posits that a higher dimensional space can be represented as a lower dimensional projection, researchers have developed models that offer a glimpse into the inner workings of black holes. These studies not only help resolve the information paradox, but also reveal deeper connections between gravity, space-time, and quantum mechanics. These advancements extend far beyond the study of black holes. If we can simulate the interactions of black holes using quantum computers, we may eventually unravel the mysteries of dark matter, the Big Bang, and even the fundamental nature of space-time itself. Through quantum computing, the possibilities for expanding our understanding of the universe are boundless. Black holes have evolved from being mere cosmic mysteries to becoming profound windows into the quantum structure of the universe itself. The fusion of artificial intelligence, AI, and quantum computing is rapidly developing into a formidable alliance with the potential to bring about groundbreaking transformations across numerous domains. AI has already driven remarkable progress in fields such as image recognition, language processing, and strategic decision-making, while quantum computing leverages principles like superposition and entanglement to perform intricate calculations at previously unimaginable speeds. The combination of these technologies holds the power to revolutionize industries, ranging from healthcare to finance, by seamlessly integrating AI's pattern recognition capabilities with quantum computing's ability to examine vast problem spaces at once. Traditional AI models, even when utilizing large datasets, face limitations and bottlenecks when dealing with exponentially complex scenarios. However, by harnessing the parallel processing abilities inherent in quantum systems, these AI models can explore multiple possibilities simultaneously, generating insights that classical hardware simply cannot achieve. This advancement could accelerate the process of drug discovery by enabling the rapid examination of extensive molecular libraries, or optimize global supply chains in real time by adjusting routes as conditions change. One particularly intriguing aspect of this synergy is quantum machine learning, where quantum bits, qubits, and quantum gates are used to store and process information in a manner that mirrors AI algorithms, but with far greater efficiency. As research in quantum neural networks continues to evolve, the applications of this technology expand to areas like advanced pattern recognition, real-time financial modeling, and even reconstructing medical images. Additionally, this integration may give rise to new cryptographic systems, creating quantum-safe AI models capable of withstanding hacking attempts from next-generation quantum computers. However, significant challenges remain. Both AI systems and quantum devices require meticulous error correction, and establishing quantum-safe infrastructure will require immense effort. Experts warn that once quantum computing reaches its full potential, AI algorithms may acquire the ability to break current encryption methods, creating a pressing need for the establishment of quantum-resistant security standards. Additionally, concerns regarding data privacy and algorithmic bias persist, reminding us that technological advancement alone is not enough to address these complex issues. Despite these hurdles, the union of AI and quantum computing stands poised to redefine innovation, with governments, tech giants, and research institutions pouring substantial investments into the development of these technologies. Each breakthrough propels the field forward, from enhancing data-driven insights to simulating the fundamental forces of nature. As AI continues to enhance our ability to interpret complex data and quantum computing expands our capacity to process it, the potential for what can be achieved in the future of technology seems boundless. This unprecedented synergy may ultimately shape the trajectory of humanity's future. In parallel, quantum computing has ignited a global arms race, as nations strive to secure leadership in this transformative technology. With the possibility of these machines becoming practically usable, governments are investing billions of dollars into research and forming alliances with universities and tech corporations. The race centers on controlling qubits, the fundamental units of quantum systems that hold the key to solving problems that classical computers cannot. Military analysts anticipate far-reaching consequences for global power dynamics. A nation that masters quantum cryptanalysis first could potentially intercept encrypted communications worldwide, thereby disrupting international relations and security. This possibility is driving a concurrent push for the development of quantum-safe encryption protocols to preemptively safeguard against the threat of quantum hackers. China, for example, is aggressively advancing its quantum initiatives, with government-funded labs and large-scale engineering projects aimed at surpassing Western advancements in areas such as quantum key distribution and high-performance supercomputing. The United States is responding with equal determination, investing federal resources into major quantum programs at organizations like DARPA, the National Science Foundation, and the Department of Energy. Meanwhile, other global powers, including the European Union and Japan, are also fostering their own ambitions, creating a highly competitive landscape. Beyond cryptography, the potential applications of quantum computing extend to accelerating the design of advanced weaponry and improving military strategies. These quantum machines could analyze vast numbers of scenarios faster than any classical system, which might also enable them to break current encryption standards, potentially leading to massive data breaches. Such threats raise significant security concerns, as breakthroughs in one country's quantum capabilities could render the defenses of rival nations obsolete. In academia, the quest to develop stable, error-resistant qubits attracts some of the brightest minds from across the globe. Private companies such as Microsoft, Google, and IBM are also vying for supremacy in the quantum race, each working on advancements in superconducting qubits, trapped ions, and topological states. The development of new materials, specialized cooling systems, and advanced fabrication methods has become highly secretive, drawing comparisons to the historical arms races, such as the nuclear arms race. While the competition fuels remarkable progress, experts caution that the lack of transparent international collaboration and agreements could lead to geopolitical and ethical risks, potentially undermining strategic stability. As each new milestone in qubit development raises the stakes, the global rivalry continues to intensify, with consequences that could dramatically alter economic power, digital security, and even the nature of modern warfare. The transformative potential of quantum computing is already being felt in fields like medicine, material science, and climate research, where it is helping to overcome limitations previously imposed by classical computational methods. In the realm of drug discovery, quantum simulations allow scientists to accurately model how molecules interact, enabling them to virtually test countless compounds in record time. This could significantly accelerate the search for cures to diseases that have long remained resistant to treatment, such as Alzheimer's and various genetic disorders. Rather than relying on trial-and-error testing, researchers can use precise molecular models to design groundbreaking medications. In material science, quantum computing offers the possibility of creating novel compounds with unique properties, such as extreme durability, self-healing capabilities, or enhanced conductivity. For instance, quantum models could lead to the discovery of environmentally friendly catalysts capable of breaking down microplastics or eliminating harmful chemicals that persist in the environment. These breakthroughs arise from the quantum system's ability to handle vast amounts of data and account for complex interactions that classical approaches cannot efficiently manage. Climate modeling is another area poised for transformative change. Existing models, constrained by classical supercomputers and limited by linear algorithms, could be significantly improved with quantum computing. By incorporating a broader range of atmospheric variables, quantum processors could generate far more accurate long-term predictions, enabling policymakers to make better-informed decisions on critical issues like carbon emissions and water resource management, potentially averting environmental crises. At the core of these advancements are topological qubits, which are engineered by manipulating exotic states of matter, such as Majorana fermions. Unlike conventional qubits, these topological qubits are inherently more resistant to noise, resulting in fewer errors and more reliable scaling. With millions of qubits on a single chip, researchers can run vast simulations in parallel, producing solutions that were once considered unattainable. This combination of quantum and classical computing forming a hybrid architecture, allows each system to specialize in solving specific aspects of complex problems. As quantum technology continues to progress, its responsible development becomes increasingly important. Scientists, governments, and innovators must work together to establish ethical guidelines, promote sustainable resource usage, and ensure equitable access to these powerful technologies. If properly harnessed, quantum computing could revolutionize fields like medicine, material science, and climate research, delivering tangible benefits for humanity and the planet. In the coming years, breakthroughs in hardware and software will only intensify, leading to collaborations that transcend national borders and academic disciplines. This collective effort could usher in an era of rapid discovery, pushing the boundaries of what is possible. At the same time, quantum computing stands at a critical ethical crossroads, demanding a serious commitment to responsible practices. The ability to break encryption, simulate entire ecosystems, and disrupt industries brings with it substantial risks. Security experts warn that advanced quantum algorithms could destabilize financial systems, exposing sensitive information on a global scale. Conversely, the potential medical breakthroughs and improvements in resource management could have an enormous positive impact. In balancing these opportunities and risks, governments, researchers, and corporations must work together to create international standards that protect privacy and maintain stability. To ensure that the promise of quantum computing is fully realized for the greater good, it is vital to develop educational programs that teach the public about the technology's benefits and dangers, including training the next generation of scientists to understand its ethical implications. Without this collective oversight, the potential of quantum computing could lead to an arms race, exacerbating inequalities and fueling security breaches. The call for responsible development has never been more urgent. By fostering open dialogue, collaboration, and ethical foresight, humanity can harness the power of quantum computing for the greatest possible benefit, ensuring that its discoveries align with our shared values.